Hey there! In this video, I'm going to teach you about quadratic inequalities, what they are, what they do, what they represent, and how to solve them. It's pretty quick. There's not a whole lot to understanding more than what you already know. But the reason why we're covering this video is because later on we're going to talk about rational inequalities, and we're going to mirror exactly what we're doing here in that video. So, what a quadratic inequality is. Quadratics are these functions that when you graph them, it gives you a parabola. Inequalities are these things that say, hey, there's an interval for which we are above, greater than, or below, less than, some other value or function. And so what a quadratic inequality does is put those ideas together. Let's take a look at our first example. So in this example, we've got x squared minus 3x minus 10 is less than or equal to 0. What this means, and this will give you a huge step up on how to solve this, what this means is, consider what this is. That's a parabola. X squared minus 3x minus 10 is an upward opening parabola. 0 is a constant. In fact, it's this horizontal straight line at y equals 0. Well, that's the x-axis. So practically speaking, this says this. Take this upward opening parabola and find out where it is below, less than, the x-axis, y equals 0, or an output of 0. That's all that this is. So really what we're asking here, all these problems that we do in quadratic inequalities practically asks, once we change them, into where's the parabola below or above 0. That's all that this is about. So we're going to be setting these on one side, greater than or equal to, less than or equal to, greater than or less than 0, figuring out where, if at all, these things cross the x-axis, which is 0, and then figuring out where we're above or below depending on the inequality that we're given. That's a rundown. So here's the things that we need to know how to do. Number 1, get everything on one side, get 0 on the other side. Number 2, be able to factor or some other way find x-intercepts. Now why? Well, if we want to know where we are above or below the x-axis, we're going to have to figure out where we cross the x-axis so that we can determine where we're above and or below it. That's really the whole idea. And so what we're going to be doing is getting everything on one side, factoring it, most likely, finding our x-intercepts, but that's not what the question asks. The question doesn't just say find x-intercepts. We're not solving that. We're solving inequality. So determining the interval that satisfies this, where we're above or below it. So in this case, it says, hey, you got a parabola, figure out where we are below the x-axis. So we're going to draw something for that. We're going to say, hey, let's say that this is our number line, or really just think of this as the x-axis. The x-axis is a number line. What we want to know is if this is an upward opening parabola where we cross and then come back up over that x-axis. That's really the whole idea. So what we're going to do out of this is we're going to take a little side step. We're going to find our x-intercepts. This is not solving your inequality. All it's doing is figuring out where you cross the x-axis and then understanding the problem is going to let you solve the inequality. So we're going to take this off to the side and solve for x-intercepts. The only reason why we're doing it is so that we can determine where we're crossing, if at all, the x-axis to determine where we are above it or below it. Keep in mind, too, that when we're solving for these quadratic inequalities, quadratics are all parabolas. So what we're going to do is we're always going to have this alternating truth statement, true, false, true, or false, true, false. Because by the nature of a parabola, it just does one thing. It just makes this U. So where we're not above the x-axis, we're below it, and then back above it. That's the whole idea. If we're upside down, a downward opening parabola, we're below, above, and then below. So in some way, shape, or form, we're going to factor this. And we understand that x minus 5 equals 0, and x plus 2 equals 0, and that says that x equals 5 and x equals negative 2. You know that I've spent a long time talking about what this actually means. What we've done here is we found where this function, this parabola, equals 0. We found where it crosses the x-axis. If this is a parabola and this is the height of the x-axis, y equals 0, the output of 0, the x-axis, then we're finding by setting an equal where this crosses. This right here does not solve this problem. It just tells you that this parabola is, in fact, going to cross the x-axis. Where? Well, if we put it in order, at x equals negative 2 and at x equals 5. Now listen, the only thing we have to do is realize what this does, whether it's upward opening or downward opening. We already know it's a parabola. So there are one of two ways to solve this problem. It's neither way is hard. Both of them work very well. I prefer the graphing way because it mimics what we're going to do later. So if you understand that that's a parabola and that's the x-axis, and we're looking for the interval below it, well, we just found out where the parabola crosses the x-axis. We know that it's upward opening, so I don't really care exactly what it looks like. We know that this parabola is really going to do this. That's the superimposition of a parabola on our x-axis. I don't care about the y-intercept. I really don't care about any of that stuff. All I care about is the interval that solves our inequality. So what this asks is, where is this parabola below, less than 0, less than the x-axis, below the x-axis? So from left to right, is our parabola below the x-axis on this interval? No, for this interval from negative infinity until -2, our parabola is above that. So that's not satisfying our inequality. Between -2 and 5, is our parabola below the x-axis? Yeah, that's exactly what you're looking for. After 5, is our parabola below the x-axis? No, it's above the x-axis until x equals infinity. Remember, with intervals, we're always going on the x-axis when we're talking about inputs, and that's what we're talking about. So we graph it and say, hey, you know what? Our parabola is less than or equal to 0 from -2 to 5. We're going to talk about brackets and parentheses in just a second, but that is what this question asks. Here's parabola, upward opening, here's 0. Where's it less than that? Where's it below the x-axis? Well, from here to here, on that interval of the x-axis. Now, depending on whether you have an equals sign or just a straight up strict inequality, we use brackets or parentheses to represent that. So when we say, hey, we want to be less than or equal to the x-axis, it includes the values that are actually on the x-axis, so -2 and 5 itself. Had we had just a less than symbol, we wouldn't be using that values. We'd say we want to be strictly less than, strictly below, but not on the x-axis. In that case, if I had given you just this less than, we use parentheses here and here. And what that would represent is that you're below the x-axis on the interval from -2 to 5, but not including those values. As it is, what I've given you says we're below the x-axis from -2 to 5, sure, but we want to include those because of that equal sign. We say, yep, those are on the x, that's the interval for which this parabola is below or on the x-axis. That's pretty much it. That is what this is talking about. The last thing I want to tell you is that there is another way to do this. If you don't like the graphing method, personally I do, it works really well for rational inequalities a little bit later. But if you don't like that, there is another way to do this. But you have to understand something about parabolas. Parabolas always alternate by the fact that they are an even function here. They're going to be because of the axis symmetry always separates our x-intercepts evenly, like perfect symmetry on that. Because of that fact, and they're even function, and they're symmetrical about an axis of symmetry, you will always get the same truth statement for intervals that are opposite. What I mean by that is that in interval here and here, they're both going to be either above or below the x-axis. There's no way parabolas do weird stuff. They only have one turning point, one sort of vertex where we come down, go up, or go up, come down. That's all they ever do. Because of that and because of their symmetry, you will always have an alternating truth to them. So we are either going to have intervals that are true, true, or false, true, false. That's all they can ever do. Now, what I mean by the true, true, and false, true, false is plug in a number. Plug in any number that you want. I'd pick an easy one like 0. Say, well, where is 0 on my interval? 0 is right here. And if we plug in 0 into our inequality, we're going to get either a true or a false statement out of that. Now, judging from that one number on that interval, we're going to get that either all of these values between -2 and 5 are true, or all of them are false. Why? Because parabolas are continuous functions, and you found where you cross the x-axis. There are no other crossing points. You don't come back up here magically and hit the x-axis and come down. We found the only two x-intercepts ever for this parabola. So when we plug in a value on an interval and we get that it's true or false, we can use it to represent the entire interval. So when I plug in 0 and go, hell, negative 10 is less than 0, that's a true statement. That means that every value in here is going to create a true statement from here to here. That's going to be true. All of those values give you an output that is less than 0. These two values give you something that's equal to 0. That's why we included them. So between here and here, you have values that are equal, then all less than 0, and then equal to 0 again. And therefore, we include that entire interval. You can do that. So if you don't like the graphing part, just plug in a number. And you get, okay, hey, that's a true statement, cool. Then understanding something about parabolas says, where I'm not below the x-axis, I'm above it. Where I'm not above the x-axis, I'm below it. And so where we have this, we go, hey, that was true because we're less than 0. Therefore, because of the fact that this is a parabola, that is going to be a false interval, and so is the other side. Those will always match up. I said that again, axis of symmetry creates a symmetrical function for us. Because x-intercepts are also symmetrical about that axis symmetry, then our truth statements, false, false, or true, true, are also going to be symmetrical. What that means is that, hey, we're not below, that means we're above here. We have to be above the x-axis here, and that fails what we're talking about. We want values that are less than 0, below the x-axis. All of these values, if I were to plug them in, are going to be positive numbers, stuff that's above the x. So those are the two ways that we really go about solving quadratic inequalities. So what's the rundown? These are all parabolas. They're always upward opening or downward opening. We find the x-intercepts. All right. Are they going to have x-intercepts? Not necessarily, but if they do, the parabola is either above then above, or below above then below. And for that reason, we have alternating truth all the time, either true, false, true, or false, true, false, depending on what inequality we're dealing with. That's it. Okay, let's move on to the next example. So we're looking at 2x squared minus 5x plus 3. Before we go any further, I want to take a look at what this really is. That right there is a parabola. It's fairly narrow, but it is upward opening. This right here is a line. It's got a y-intercept of 3 and a slope of 5, so it's a fairly steep line. Here's what this asks. It says, given your parabola and given your line, and let's suppose they cross, which they do, where is your parabola below the line? That's all this stuff is talking about. You can look at it. Here's going to be an x value. Here's going to be an x value. Where's our parabola below the line between these two? That's where it is. So we're going to translate this problem a little bit. You could have talked about where's it above the line, and that would be this interval and this interval, where the parabola would be above the line. We're always talking about x values, but that's what this picture is. Now we can cheat this just a little bit. Instead of talking about the parabola and a line, we can get everything on one side in order, first your positive and 0 on the other side, and translate our problem just a bit. Instead of talking about a parabola being below a line, if we subtract the 5x and subtract the 3 and get 0 on one side, we can translate this problem to, well, we're not talking about a parabola and a line anymore as far as having a diagonal line. We'd be talking about a parabola and the x-axis. And the values of x are going to be the same. Where this parabola crosses this line, or where the parabola we're about to get crosses the x-axis, are going to be the same values. So we sort of kind of trick the problem a little bit. So let's do it. Let's get everything on one side. Let's get it in order. Let's get the first term positive. This sounds pretty familiar. This is still a parabola. Hey, it's still upward opening, and there's a 0 right here. So what this says is, if I draw an x-axis, if this is an upward opening parabola, and let's suppose that it crosses the x-axis, there are going to be two numbers where this parabola crosses once and then comes back up. If it crosses, it comes back up and crosses again. What we're going to do is we're going to find these numbers. How? We're going to factor it. Factoring does not solve this problem. It gives you the x-intercepts so that you can interpret it and solve the interval for which your parabola is now below 0, below the x-axis. It's gonna be this interval. Do you see it? Do you see how our parabola is above in this interval, below in this interval, and above? We're not asking for above. We're saying where's this upward opening parabola below, okay, underneath the x-axis, this 0. That's the same exact thing as saying where's this parabola below that line. That's all we're doing. Let's go ahead and factor this. So at this point, as long as we know how to factor, I really don't care what method you use. Me personally, I do a -5 and a -6. Think about this as -6 and +1. Hey, let's see, that adds to -5, that multiplies to -6, so we have that right. I would probably divide by my a. And at this point, you can be done. If you simplify this and say that's -3/1, and you change your signs, you've already found your x-intercepts. We know that this is going to intersect our x-axis at +3 and -1/2. Now, if you want to go ahead and do the whole zero product property, factor this all the way out, that's totally fine. But again, that's not the idea here. The idea here is you are only finding these values so you know where to put this on your x-axis. So I would say that this is -1/2 and +3. That's all we're using that for. These do not solve that problem. They just tell you where your parabola crosses. And that's it. Now we interpret it. Okay, how do I interpret it? Look here and imagine that this is a parabola. We have sort of an image of that. Does it cross our x-axis? It does here and here. Now find out where this does this to that, where this parabola is less than 0. In this interval, no, that's false. On this interval, is a parabola less than 0? Yes. So from -1/2 to 3. So we use interval notation here. That's pretty standard. You don't have to. You can do inequality notation if you really want to. So you can do -1/2 less than x less than 3. But interval notation is fairly standard. Now let's also determine whether we need parentheses or brackets here. Because we say strictly less than, we don't want to include the values that are on the x-axis. That would be less than or equal to. So I don't want to include -1/2 because that is saying where this parabola actually intersects the x-axis. So I'm going to disinclude that. How we disinclude a value but include everything past it is with parentheses, and the same thing with 3. So what this says is this parabola is strictly below the x-axis, just past x equals -1/2 and just before x equals 3, just excluding those individual points. That's why we don't have a bracket. Now the other way, pick 0. Take 0, find out where 0 is. There's only one time you can't do that, and it's if you don't have a constant. So because one of your x-intercepts will be 0 in that case, you can't plug in 0. Otherwise, find out where 0 is. It's somewhere in this interval. So pick 0 and plug it into your inequality. -3 is less than 0. That's a true statement. That says that everything on this interval is true. There's nothing in here that's going to give you a value that's greater than 0. Why? Because parabolas are continuous functions. You found the two places where they cross the x-axis, hence equal 0. So we're either above or below 0. And because we don't have any other x-intercepts, we can't change the sign on anything in this interval. They will all be positive or all be negative. Every value between -1/2 and 3 is a negative output for this parabola. That means that they're all below 0. This parabola is below the x-axis. That's a true interval, and that's exactly where we get this thing. We say, hey, this interval is true. This satisfies my inequality. Let's write the interval, and then we do this again. Now, because we have parabolas, yes, you can assume they alternate because parabolas are, again, continuous functions, and once we cross the x-axis, we don't come back again. Every value from here on out, when I input it into my parabola, is going to be positive. That's above the x-axis, and that does not satisfy what that is. So the interesting thing is that this interval that says where this parabola is below the x-axis is the same interval where this parabola is below that line. We just got everything on one side so that factoring worked very nice for us. I hope that makes sense. I hope you're seeing the nature of parabola, we're figuring out where it crosses something, and then determine where we're above or below. There's two ways to solve it. One is just graphically, understanding the graph. It's a parabola, it's pretty easy to understand. Or, excuse me, plugging in a value and alternating our truth. Let me use a word of caution here. When we get to rational inequalities, I'm going to show you this again. I'm going to say that it's possible to determine where we alternate and where we don't. by what's called multiplicity. So we're going to reference that, or the evenness and oddness of vertical asymptotes. We haven't talked about that yet, but I'll reference that again. So we're going to be thinking of graphs and doing practically the same thing. It's kind of fun, actually. Other than that, that's about it. We're going to do two more cases. The last question I often get is, why don't you have any negatives? Where's your downward opening parabolas? Where are those at? It doesn't really matter. And the reason why it doesn't matter is because if you had a downward opening parabola, you could change the signs, get everything on one side, first term positive, and even though it wouldn't be downward opening, your inequality would also be different. So asking where a downward opening parabola is above the x-axis is the same thing as asking where an upward opening parabola is below, and your inequality would bear that out. So if you follow the technique, get everything on one side in order, first term positive, and 0 on one side, we'll still get the correct interval. It gives us a slightly different picture, but it doesn't matter if we're just looking at the interval. Now, getting the original picture correct, understand what's going on, yes, that is important, but maybe I can show you one right now. So suppose that we had that's our first example with everything flipped around. So negatives instead of, negative x squared plus 3x plus 10 greater than or equal to 0. So if I said, hey, I want to get everything on one side in order first term positive, that's not positive. What is that? That's a downward opening parabola. What's that? We're asking where it's above the x-axis. So this picture would be a downward opening parabola above the x-axis. Could you still find out where it crossed the x-axis? Yes, but we'd factor a negative, or we'd change all our signs. The thing about inequalities, though, is that if you factor a negative, and you change all your signs, if you divide by a negative in order to get this negative away, let's say, then when you divide by a -1, it changes your inequality. Do you remember that when you divide by a negative, you flip your inequality? And what I'm trying to show you here is that regardless of how we approach this problem, the interval is going to be the same. We just made that problem out of that one. So even though that's an upward opening parabola, that's a downward opening parabola, and that's an upward, and we have this 0, one's greater than 0, one's less than 0. This sort of proves to you that a downward opening parabola above the x-axis is going to have the same interval as the upward opening parabola below the x-axis. You'd solve it practically the same way. If we wanted to stick with this version and say, hey, this is still, let's see, x equals -2, x equals +5. If we wanted to stick with this inequality, that would be a downward opening parabola, but you'd be looking above. You'd say, hey, on what interval is this downward opening parabola above the x-axis from -2 to 5? Or, like we did before, if you want to consider it this way, on what interval is this parabola below the x-axis? It's the same interval. This would be true for the downward opening. This interval would be true for the upward opening. I hope that makes sense. There's two ways to really look at this. You're finding the same interval. They would have the same truth. The main thing here is that if you are going to divide by a negative, though, you do have to change that inequality. That's a big deal. The other way to do it would be to add x squared, subtract 3x, and subtract 10. But you can see this asks the same question. Where is 0 above our parabola? Or where is our parabola below the 0? And that's the same exact thing as a solid parabola we've drawn. So that's where I'm going to leave you at. The main point here is that if you want, you can always make your parabola have a positive first term, and you'll find the same interval of truth. The picture will be a little different. So if that bothers you, maybe try the interval instead of doing the picture. But the process bears itself out. So just mind your pictures, be careful on what you're drawing, understand the concept of what's going on, and you'll be just fine. Let's move on to the next couple problems. All right, last two. Let's look at what's going on and then see if we can solve these inequalities. Number one, that's a weird looking inequality. Maybe we should distribute this to get a better picture of what's going on. So x squared plus x, always it's a parabola, and we're asking where is it above this horizontal line at 20? So what this says is here's this horizontal line, that's a constant. We're going to have a parabola that's upward opening and asking where is this above that 20? So if this is a height of 20, and we have this upward opening parabola, we're figuring out on what interval is this above it? Is it above between the crossings or outside of the crossings, if you want to call it that? And you say, oh, that's outside. We should get kind of an awkward interval. Something where for a really long way we're above 20, then we're not, and then we are again. This alternating truth statement. Now, how we're going to solve this problem is we're going to shift this parabola down 20. We're going to subtract 20 from both sides. And this is going to translate to, instead of thinking about a parabola below a height of 20, we think of a different parabola below a height of 0. In other words, where this upward opening parabola would be above the x-axis. That's what we're thinking of. I mentioned something in the last example. Could you have considered this to be a downward opening parabola? You could have. We can just change all of our signs if you want to, and this would have the same truth as negative x squared minus x is less than negative 20. By multiplying everything by negative 1, yes, you have to change your inequality, but this would be a downward opening parabola. This would say, where's your downward opening parabola below negative 20? That's what that would do. So I would say between this interval, oh hey, it's the same exact interval, and this interval. That's what's going on there. So back to this. Because we're seeing out where this is above our x-axis, we're going to be thinking, you know what, hopefully it crosses. If it does, excellent. We can find our two x-intercepts. We can find that this is upward opening parabola, take a picture of it, put it on that graph, and figure out where we're above. So if we know that x squared plus x minus 20 is factorable, this is x plus 5 and x minus 4. We can do it a number of ways. It doesn't really matter how we do it as long as we can factor correctly. Then x would equal negative 5 and x would equal positive 4. This does not solve this. It simply tells you, because it's a parabola, where you cross the x-axis. Now we're going to take our picture. That's an upward opening parabola. We're going to graph it. We're going to now understand the problem. The problem says, I want you to find me the interval where your parabola is above the x-axis. Where's your parabola above the x-axis? Here's the only 2 points in the world where we're on the x-axis. Every place else, we're either above it or below it. That's a huge interval. That's all of this to negative infinity and all of this to positive infinity. How we write that interval, we write from the left to the right the correct interval. We're above the x-axis until we get to negative 5. And then we're below the x-axis. We're going to disinclude this interval. We don't want that. And then we're above again from 4 to infinity. These are the 2 intervals where we are above the x-axis on that parabola. That's what we want. That's what this translates to. Now, do we include endpoints? Well, because that's not an equal sign, this says, I don't want you to include where we're actually on the x-axis. I want you to disinclude these 2 values. We use parentheses for that. We use parentheses for infinities all the time, so no matter what. And then we put a union, saying it's this interval sort of combined with or this interval. Those are the 2 intervals that are going to create true values for this inequality. And that's what we're talking about. The 2 intervals where a parabola is above the x-axis. Had that been an equals, the only change here would be that you would include brackets on your negative 5 and your 4. It's all that would change, not your infinities. The other way, if we want to understand that parabolas alternate truth, take your 0. Plug in your 0 here. If I do that for my inequality, 0 plus 0 minus 20 greater than 0, that's a lie. That's not true, that's false. That says this is a false interval. Nothing in this interval is going to have a value that's greater than 0. They're all going to be negative. You can see it. Well, because these are parabolas, then our outside intervals, outside of those x-intercepts, those would be true. Negative infinity, negative 5, and then 4 to infinity again. That's the way that we solve these. taking a look at the last one, this is kind of a weird problem. This has a parabola to it, so this looks like a parabola. This is, let's see, a line with a fairly steep slope, and this asks, where is this parabola below the line? We can translate that. We can translate that to, where is this different parabola below the x-axis? It's the same idea. It's going to give you the same interval. It's just kind of manipulating the shapes a little bit. Instead of parabola line, you have different parabola and the x-axis, but we're going to get the same thing. We did something very similar to with the intercept idea. Like how we find where functions intersect is by setting them equal and then sort of considering a different problem, but we get the same intercepts. And that's what we're doing here. So when we look at that, you go, wait a minute, that doesn't look super factorable. So 4x squared, that's a parabola, it's upward opening, minus 6x plus 9 to be negative 6 and 36. I'm not seeing how to get negatives, add to negative 6 and multiply to positive 36. So what do you do when you can't factor? Well, you either complete the square or you do quadratic formula. You go, okay. All right, well, quadratic formula is going to be kind of nasty. If you had to do it, you could certainly find approximations, couldn't you? And you could figure out where you're above or below, depending on those approximations. It's not super relevant what numbers are here as long as you're able to find those numbers. I guess it is relevant that you want the right numbers for your interval, but what I mean is that you don't use them to solve your the inequalities as far as true, false, true. We can understand the picture of the graph to get the true, false, true, or false, true, false. Here we'd say, all right, well, I don't even have x-intercepts yet, so let's do the quadratic formula. We know that quadratic formula says that we can do x equals negative b plus or minus b squared minus 4ac, all divided by, I'm going to get a 4 there anyway, all divided by 2 times a. Now I would typically do my b's, then my a's, and then my c. I don't care about this. I care about that right now. Because here's what's going to happen. What's going to happen is that inside my radical, we have 36 minus 4 times 36. 144. All over 8. I hope that's 144. 36 and 72. 72 times 2 is 144. All right. What's going to happen there? Well, we got 36 minus 144. That's a big fat negative. What's a big fat negative mean in a discriminant? We got to know that big fat negatives and discriminants mean that you don't have any x-intercepts. So wait a second. How can you have an upward opening parabola without x-intercepts? It has to look like this. Here's what this says. Picture this. Visualize this. That's your x-axis. This is an upward opening parabola. We're asking, where's this upward opening parabola less than 0? But we just found out this upward opening parabola has no x-intercepts. This discriminant is negative. It's going to give you an I. It says that you do not cross the x-axis. Are you seeing why I spent so much time talking about what you are doing when you're factoring, or square root method, or quadratic formula, or completing the square? You're finding x-intercepts. And so if we find that our imaginary numbers here cause a complex solution which says you don't have them, then this upward opening parabola has to be like that. If it does not have x-intercepts and it's upward opening, it's floating above the x-axis. So answer the question. Where is this parabola below the x-axis? It's not. There's no solution here. There is no interval where this parabola is ever below 0. There are no values you can plug in there to give me a negative number. No real numbers at all. That's what that's doing. So I hope that you're seeing that picturing the parabola, picturing the less than 0, what the x-intercept represents, is very helpful. Now, could you have done it by just plugging in a number? Yeah. If there's no x-intercepts, you find that out and you go, well, plug in 0. 4 times 0 minus 6 times 0 plus 9 is less than 0. It says 9 is less than 0. That's false. That says, wait, false. What interval is false? The whole thing. Because we don't have any x-intercepts, there's no place where our sign changes. There's no place where we're above than below than above anymore. It would have the same truth for the whole interval. Here we had 3 intervals. Here we had 3. All other places we had 3. This has 1 interval because we didn't cut it up. We have no x-intercepts at all. We didn't cut that interval at all, and so this whole thing will have the same truth. It's either all going to be true or all going to be false. That's the 2 ways we can approach it. Imagine your graph, imagine your x-axis. We have no x-intercepts. You're an upward opening parabola floating above. You can also do the same thing if you change all your signs, a downward opening parabola floating below. So if you change negative, plus, minus, and switch this to a greater than, it'd say, where would your downward opening parabola be above the x-axis? And you wouldn't be. It'd still give you false for everything. It'd still say there's no interval for which you are positive. You would always be negative. That's what's going on. Now, what would happen if we changed the inequality without changing the signs? We just said, hey, imagine this. Greater than. Is 9 always greater than 0? Is this parabola always above the x-axis? Yeah. If we change the inequality, then this asks, where is this parabola, which is upward opening, above the x-axis? And it doesn't have any x-intercepts still. There's still nothing there. You see the quadratic formula. You still see there's no x-intercepts. You still say, hey, that's a parabola. It's upward opening above the x-axis. There is no place where this parabola isn't above the x-axis. This would be true for the entire interval. In fact, since we don't break up the interval at all, this would be from negative infinity to infinity, or all real numbers. So depending on how that sign is, we either have, the inequality is, we either have no solution floating above, asking where it's below, or infinite solutions floating above, asking where it's above. And that's the idea. I hope that I've made this make sense. Hope you understand the picture of the parabolas. Getting that your number line is just the x-axis. It's the easiest way to picture that. You can do it other ways. You can find x-intercepts and do the true-false-true thing, plug in some values for your intervals. That's great. I used to teach that way a long time ago. But picturing the graphs tends to stick with students a lot better. And later on, when we do rational inequalities, it's going to make a lot more sense because we'll talk about multiplicity. And we'll talk about even and oddness of vertical asymptotes, and I can make these things work really well if you understand the picture version. So I hope I've explained it well enough for you to understand, and I'll see you for the next video when we do a few examples of some applications.